Welcome to Control4 Driver Development Essentials. My name is Peter Casenza. In this video, we will walk you through the steps required to create a Control4 driver for an audio-video switch. In doing so, we'll use two tools delivered by Control4 to assist with driver creation. The first is Driver Editor version 3.0. This latest version of Driver Editor is a driver development environment that provides a graphical interface for the creation and modification of C4Z files. It is important to understand that Driver Editor 3.0 and all subsequent Driver Editor releases are compatible with C4Z files only. If you are new to C4Z files, we'll discuss them in the beginning of this video. The second tool we'll use is Control4's Audio-Video Switch Driver Template. Control4 is currently in the process of delivering driver templates for many of its more heavily used proxies. Driver templates are delivered with Driver Editor. When a template is selected and loaded into the Driver Editor environment, it offers a powerful development scenario that can reduce development time as well as improve code quality. In this video, we will use a template specifically designed to help create an AV switch driver. In viewing this video and all videos found in the T201 series, it is expected that you be familiar with the architectural and development concepts outlined in the driver development training modules. This includes the 201, 301, 401, and T101 video series. You may find it useful to review the information offered in those training modules before proceeding to develop template-based C4Z files. Before we begin creating a driver for an AV switch, it might be useful to briefly discuss C4Z files. Beginning with Operating System 2.6.0, Control4 has changed the file structure previously used to support device drivers. Up until 2.6.0, device drivers were contained within a single file using the extension of C4I or drivername.c4i. The release of 2.6.0 marked a significant change to this model with the introduction of the C4Z file structure or drivername.c4z. A C4Z file provides all of the content that the C4I file previously did. However, it offers some significant features and advantages that its predecessor did not. At its most basic level, a C4Z file is a zip file. It contains numerous folders and files which, when encapsulated inside a C4Z file, represent a device driver. The modularity within the C4Z file enables a far more organized and structured approach to device driver architecture. It also provides the ability to include many related objects within the confines of the driver in an organized manner. These objects include items such as graphics and icon directories to support custom user interfaces which can run on Navigator. A C4Z file also includes one or more Lua files, which contain all of the driver's Lua code. Control4 driver templates take advantage of the C4Z structure by delivering libraries of commonly used Lua functionality. These can now reside in one directory location and can be easily referenced. A C4Z file also has its own XML file, which separates the XML portion of a driver from the Lua code. Additionally, rich text documentation can be included in the C4Z to support a far superior user assistance model. Now, let's talk more specifically about AV switches. Before we get into the nuts and bolts of AV switch driver development, let's talk about some of the terminology you'll hear while watching this video. Here, we see a listing of key terms that must be understood to properly develop your AV switch driver. All but the last item relate to the type of signal routing that is supported by the device for which you are developing a driver. The first two, audio only and video only matrix, are the most simple since they are only handling one signal type. This will become more obvious later in this video when we discuss modeling AV connections. The next item, basic audio video matrix, handles both audio and video signal types but they cannot be routed independently. So from our driver perspective, they need a little more work when defining the connections, but from a control standpoint, they are not really more complex than audio-only or video-only matrices. Now, on to a little more complexity. The audio-video matrix with separate audio and video switching. In this case, the driver must include logic to process routing commands of audio signals separately from routing commands for video signals. Obviously, this logic will be dictated by the protocol of the device for which you are writing a driver. Finally, for the greatest level of complexity is the HDMI switch with analog audio breakout. This complexity is partially due to the advanced functionality that these devices deliver, and partially due to some nuances and limitations in the Control4 system. Advanced functionality delivered by some devices include taking an HDMI signal from an input and routing that to an HDMI output, and also routing the audio portion of that signal to an analog audio output. The converse may also be true, where an analog or digital audio only signal connected to the input may be output to an HDMI output. This is particularly useful on devices that support HD-Base-T. It is important to know that some of these scenarios are beyond the scope of this video. We will cover the more advanced topics in separate videos. You can also post questions to the Driver Development Forum. The last term I would like to mention is volume ramping. Volume ramping typically occurs when you press and hold the volume button on a remote control. The volume will continue to increase or decrease until that button is released. The Control4 proxy volume implementation is very basic. It issues a pulse volume command for quick button press releases. For a press and hold sequence, it issues a start volume command on the press and a stop volume command on the release. The protocol driver must supply all other logic. One caveat to consider is that some mobile navigators do not use the start volume, stop volume commands due to the possibility of a runaway event if the stop volume command gets lost. In these cases, a series of discrete set volume commands may be sent. The last item to consider before we begin driver development is the protocol information for the AV switch for which you wish to create a driver. It is important to obtain the latest protocol document from the switch's manufacturer. It will provide you with the device's communication syntax and notifications it will send to the Control4 AV switch proxy. Now, let's open up Driver Editor 3.0 and take a look at the AV switch template and discuss what's required to write an audio-video switch C4Z driver. From within the Driver Editor toolbar, we'll select File and hold our mouse over the New menu option. Here, we are presented with several choices. In this demonstration, we're going to create a new driver project, or C4Z file, based on an existing template. So we'll select the Driver Project from Template option. When we do so, we can see the AV switch proxy template. At this point, it's worth explaining a driver editor construct that is important to understand. Driver Editor 3.0 views C4Z files as a project. When a C4Z file is loaded into its environment, it organizes the C4Z into a structured project and displays it in the driver project window. Due to the organized structure of a C4Z file, it's easier to consider our driver as a project while working in the Driver Editor 3.0 environment. This is also a good time to discuss where Control4 driver templates reside on your system. Driver templates are delivered by Control4 through the Driver Editor development environment and will always reside in the following directory under Program Files. You will also find a driver template directory in this location under the User's Documents directory. This directory is created for you to store driver templates that you have customized or created on your own. It is important to keep these templates separate from the Control4 supplied templates, as the Driver Editor Templates directory is overwritten upon an update of Driver Editor. The first thing you'll notice is the driver project area of the screen. Here is where we can see the project framework that is provided through the AV switch template. While at first glance it may seem like there are lots of files and directories, it's actually numerous Lua files organized by purpose. You'll note that some of them are in libraries as well. Here is our driver's XML file and also driver documentation in a rich text file. If you are familiar with the C4I file structure, you'll remember that all of this would have previously resided at one level within the confines of a single C4I file. If you want to open one of the Lua files in the project, simply click on it and its contents are displayed in Driver Editor's editing window. For example, let's open the project's main driver.lua file. This file is significant as it contains all of the require statements for our driver, as well as the initialization code that is executed when our driver loads. We can also see our driver's XML content in the window by opening the driver XML file. When we double-click the file, we can see the high-level XML in the driver configuration window. Many of our driver's XML information is edited by double-clicking on any of the top-level elements. This displays Driver Editor's XML editing screen. Here, numerous XML entries can be modified and easily saved in our driver project. The more complex XML elements can also be opened and edited in the driver configuration screen. For example, if we open the proxy's XML entry, we can see a high-level view of its contents. Double-clicking on the proxy value will display the proxy editing screen where changes can be made and saved into our project. You will find that the UI in Driver Editor presents XML based on the data types and amount of data that a particular element contains. For example, if we go into Capabilities and double-click on the Audio Consumer Count element, the Driver Editor screen will display a window to add, delete, or edit capabilities that your AV switch supports. Let's go back into Driver Project and look at one more file. I can toggle between Driver Configuration and Driver Project by using the tabs at the bottom of the Driver Editor screen. Here is the documentation RTF file. Double-clicking on the file opens an editing screen which supports rich text formatting. Font assignment, images, and hyperlinks are all supported in this area. This provides you with an excellent opportunity to deliver quality driver documentation to integrators who are using your drivers in commercial or residential systems. Now, let's begin to modify this template and turn it into a publishable C4Z file which supports an AV switch. In this section of the video, we'll show you examples of each of the development steps to complete the driver. These include handling proxy notifications from the AV switch to the Control4 UI, handling proxy commands from the Control4 UI to the AV switch, including device-specific commands that fall outside the scope of the Control4 proxy, updating the XML for the driver, modeling audio-video connections, adding documentation to support our driver, building the driver in Driver Editor, validating the driver in Driver Editor, and finally, publishing the finished C4Z file. To start, let's look at a data flow example and see how the AV switch driver template handles communication coming from our AV switch to the Control4 user interface. We call these data messages notifications. This work happens in the device messages.lua file found in the driver template. Let's take a closer look at this file in the Driver Editor environment. All messages sent from an AV switch need to be parsed into a format that the Control4 AV switch proxy can understand and ultimately be handled correctly by your driver. These messages contain data that directly impacts what is displayed on the system user interfaces through the use of AV switch proxy notifications. All of the proxy notifications are predefined for you in the AV Switch template. They can be found in the AV Switch Proxy class Lua file. When we open this file and scroll to the bottom, we'll find all of the AV Switch Proxy notifications. They are under the AV Switch Proxy Notifies header. There's no need for you to edit any of these notifications. They are called after you parse the messages from the device and then create a new function that passes the parsed data into the AV Switch Proxy class Lua file. The new function that you create will call one of these predefined notifications. The notification is then sent to the proxy using the Send to Proxy API. This results in the system user interfaces being updated with the message data from our AV switch. All parsing of data messages from our AV switch occurs inside the device messages Lua file. If we open the file, we can see that sample functions have already been included for you. Note the use of to-do in the functions. These serve as informative descriptors to help you find the areas in code that need your attention, as well as understand what type of data the function handles, and possibly any parsing considerations. Perhaps the most difficult job for you as a driver developer will be to parse the incoming messages from the AV switch into a format that can be sent to the Control4 proxy and displayed as usable data on the user interface. If the AV switch sends multiple messages within one packet, each message must be parsed so that it can, in turn, call a unique notification function that correlates with the message type. All parsing of device messages is done using the handle message function, which is also in the device message Lua file. Here it is at the top of the file. Let's consider, for example, that our AV switch sends a message whenever the volume level is changed. We want to use the data in that message to update our UIs with the AV switch's latest volume information. The incoming message from the AV switch might look something like this. The protocol for the AV switch with which we are working uses a 3-letter prefix in its messaging that indicates the functionality of the message. In our example, VOL means volume. Next, the protocol sends a number which represents the zone whose status is being reported. So here, the number 1 indicates that the message is applicable to zone 1. Next, a colon delimiter is sent separating the zone data from the volume data. Finally, the protocol sends a value at the end of the message. In our case, the current volume level is 50. And we know from reading this particular AV switch's protocol documentation that the message values sent regarding volume levels are in percentages. Without modification, this means nothing to the AV switch proxy. We first need to parse the incoming message into a name-value pair, with the name being the command from the device and the value being its parameter. Once the data is correctly parsed into name-value pairs, we need to create a new vol function for this message. The value is passed as a parameter to our new function, and at this point it can be handled by the AV switch proxy. The AV switch proxy class is defined in the AV switch proxy class Lua file. This file provides a template API or a group of functions that can be called by our newly created vol function. All of these APIs are recognizable by the AV switch proxy and can pass the data on to our UIs. The names of these API functions begin with DEV_. For example, here is the function for handling the AV switch's volume. It's called dev_volume level changed, and it has 3 parameters. Output, which correlates to the connection output bound to the zone whose volume is changing. C4 level, which is the current volume level expressed in the Control4 volume range, which is percentage. Device level, which is the current volume level expressed in the device's volume range. This could be percentage, but in most cases it will be in an audio scale. Knowing this, we need to go back into the device message Lua file and build a new function that is based on the vol message from this device. In this example, we'll make the assumption that the message coming from the device adheres to the same volume percentage scale that is supported through the Control4 AV switch proxy. The new function we need to create looks like this. Based on this example, we can see that our protocol uses a colon delimiter within the string of the message. Let's look at the function line by line to understand how it handles volume level, so the Control4 proxy can pass the information up to the system user interfaces. Note that line 1 contains a reference to the Lua table dev_MSG. This table holds all of the functions handling messages coming from the device. Following the dot, we see the name of the device function, or VOL. This is the name portion of our name value pair. This is followed by the value portion of our name value pair. It is the data in this variable that will eventually be passed as a parameter up to the UI. In this line, you would handle any conversion that may be needed to parse the incoming parameter into the correct volume and zone formats for the AV switch template. Here, we see an example of the Lua string match function, which is part of the Lua string library. If you are not familiar with string match and the other functions in the Lua string library, you can find full documentation at lua.org. What you will find particularly useful is the use of captures and patterns in Lua string functions. Understanding these conventions will greatly simplify your driver's parsing code. In our example function, string.match is used to capture the number before the colon and return it to a variable named device output, and then capture the number after the colon and return it to a variable named device level. So at this point, we now have the output ID and the volume level based upon the ranges defined in the device's protocol. The next line of code is where we would convert these values into the value ranges required for use in our proxy. In this example, we are assuming that no conversion is necessary, so we will merely pass the values directly from the device variables into the new variables named output and C4 level. While this may seem redundant from the perspective of this example, being explicit will make your code more readable and also more portable. Finally, we see a call into the AV switch proxy class Lua file and its appropriate API named dev_volume level changed. As you can see, this function takes 3 parameters, the output ID and volume level in the Control4 range, as well as the volume level in the devices range. This example contains all the logic needed to create a notification. When the call is made, the template API dev_volume level changed will take the parsed and possibly converted variable from the AV switch and pass it on to the AV switch proxy, which will notify the UIs of the current volume level, which in our case is 50. It also stores the volume in the device's range for use in future volume ramping sequences. Now, let's change direction and take a look at communication flow coming from the Control4 UI to our AV switch. When we refer to Control4 UI, we're talking about the initiation of an AV switch message being sent to the AV switch from our user interaction through any device running Navigator or Composer Pro's control. We call these messages proxy commands. When a message is initiated, it first calls Control4's AV switch proxy. The proxy then calls into the Control4 API received from proxy, which, in turn, calls into the AV switch proxy commands Lua file using the PRX_CMD command table structure. AV switch proxy commands Lua is a template file that receives the command from the proxy and handles it for you, the driver developer, by modifying its format as well as its parameters. For example, PRX_CMD.command name, which takes binding ID and tparams as parameters, and that in turn calls PRX_command name with tparams as a parameter. The AV switch proxy commands Lua file then calls into the AV switch proxy class Lua file. This template file stores device-specific data within the driver template. It receives the modified command and extracts its tparams table into one or many individual parameter elements for you. In doing so, it also modifies the format of the command further. For example, PRX_command name takes a tparams table as its parameter, and in turn that calls command name with each of the table entries in table parameter sent as individual variables. This modified version of the command is then delivered to the proxy commands Lua file. Here is where you, the driver developer, needs to receive the command and its parameters, modify them in a manner that is valid for the device, and subsequently send the command to the device via the designated communication method. Now, let's take a look at an example of the functions that are included in the proxy commands Lua file. In doing so, you will see how the AV switch template uses Lua tables to store most of the data required to build functional commands. By using tables in this manner, we are able to keep the actual function code in small, easy-to-read code blocks. Here we see the setInput function as it is delivered in the template. You will notice that it supports IR control, which will not be addressed in this video since it uses a very different command structure than the serial and IP drivers. So, for serial and IP drivers, there is only one line that you, the driver developer, will need to modify. As we drill into that line, we see that there are three main components. First is the command variable, which will store the command string that will ultimately be sent to the device. The remaining two elements are what are used to build the command. Since most AV switch protocols will use the same syntax for input selection, all we need to do is store output string elements in one table and the input string elements in another table. These tables will be indexed by the output connection and input connection IDs. So, when the command is sent by the proxy, it will take these IDs to the respective tables and get the correct input and output component and assemble them using the correct syntax for this device. For this example, let's assume that the protocol for input selection uses this syntax: O, X, I, Y, where X is the device's ID for the output and Y is the device's ID for the input. Let's also assume that the device IDs start at 1 and our driver's connection IDs start at 0. Here is our modified function. And here are the tables to support this function. The output command map table maps the value of the output connection ID, which has been modded by 1000, to the output command elements used by the AV switches protocol for input to output routing. The input command map table maps the input connection name used by Control4 to the input command used by the AV switches protocol. The input command map by ID table maps the value of the connection ID, which has been modded by 1000, to a name value which includes the Control4 input value and the proxy binding ID for this device, which is stored in the constant AV switch proxy binding ID in this case. If you were paying attention earlier when we examined our modified function, you may have noticed a small twist to the input part of the command string. Here we actually reference two tables. This enables us to translate the proxy command, which uses the connection ID, to the device command table, which uses the input name. Finally, we need to review the pack and queue command function, which will take this command, pack on any prefix or suffix if required, and then send the command to the device. Okay, let's take a closer look at the pack and queue command. First, you will notice that this function has 3 dots for parameters. This is the Lua notation for optional parameters. This function is expecting up to 4 parameters, but you really only need to send the first 2. The first parameter is the name of the command that is calling this function. The second parameter is the actual command string that needs to be packed and sent. The third and fourth parameters deal with the amount of time that the command queue will wait after sending this command and before sending the next command in the queue. This time interval is referenced as the command delay in Control4 templates. All templates have a driver property that sets the default for this time delay in milliseconds. So, if you want to use the default value for any given command, you do not need to send the third and fourth parameters to the pack and queue function. If you do want to override the default values, you can use the third parameter to override the number value of the delay, and the fourth to override the default time units. For example, you may wish to use units of seconds or minutes for certain commands like power on. Keep in mind that you should not change any of these lines of code as they are ready to go as is. Next, we get to the packing part of this function. Most protocols employ a syntax that require a terminating character or set of characters at the end of each command string, like a carriage return or a carriage return in a line feed. Since this is required on every command, there is no need to add it to each command table and command function in your driver. Simply define it once here in the pack and queue command and be done with it. The same logic also applies to any start character or set of characters that may be required. Also, some protocols use the same command strings for serial and IP communication, but may require different start or ending characters. Pack and queue command is already set up to handle that for you. And finally, we see a call to the queue command function in the connection class. At this point, our command is pushed onto the command queue. The command queue will take care of sending the command and popping the command off of the queue automatically. The setInput function that we just reviewed is a good example of the multi-zone type functionality that needs to be supported in an AV switch driver. And we also saw how Lua tables make it easy to store the command information in a building block type methodology, which makes the function code easy to read and manipulate. But what about the commands that are not multi-zone in nature, such as menu navigation commands? The AV switch template greatly simplifies the handling of those types of commands. All you need to do is fill in the correct command string in the CMDS Lua table that is included in the template. Now, let's look at another example where the AV switch does not adhere to Control4's AV switch proxy's use of a volume percentage scale. In this example, the message coming from the device also uses a colon delimiter, but the message values for the output ID and the volume level need to be modified so that the proxy can understand them. Consider that this AV switch sends a volume message that looks like this. The new function to handle this message would look like this. Once again, Let's look at the function line by line to understand how it handles volume level so the Control4 proxy can pass this information up to the system user interfaces. You will notice that the line at the beginning where we parse the device message using string.match and the last line where we call into the AV-switch proxy class have not changed. This makes sense since we're assuming the same device message syntax, and of course the AV-switch proxy API call requires the same parameter values. What is different in this example is the processing that we need to do with the device variables in order to convert their values to the applicable Control4 values. First, let's look at the output ID. Keep in mind that in Control4 templates, the output ID is the mod 1000 value of the actual output connection that you have defined in the XML connection section of your driver. For this example, the driver's output connection IDs start at 0, and the device protocol starts the output IDs at 1. So for any given output, we will need to subtract 1 from the device output ID when we wish to reference it in the Control4 driver. Next, we need to convert the volume level. In our example, the device is using a volume scale that starts at -80 and goes to +20, whereas the Control4 volume range is 0 to 100. To do this conversion, we will use a helper function that is delivered as part of the AV-switch template named convertVolume to C4. This function takes 3 parameters: the current volume reported by the device, the minimum value in the device's volume range, and the maximum value in the device's volume range. The function processes this data and returns the converted volume value in the Control4 scale. To make this function more readable, the template includes 2 variables where you can enter the device's min and max values. We already have the device level, which was parsed in our string.match line. Next, we see that convertVolume to C4 takes these values and returns the converted volume level and stores it in the C4 level variable. And finally, these values are used by the AV-switch proxy function dev_volume_level_changed to update our proxy with the current volume level. Once we have handled all of the messages that the AV-switch sends, which require being set up to the UI in this manner, the Lua development work for handling proxy command messages in our driver is complete. In our next example, we will see how the AV-switch template can handle device-specific commands that fall outside the Control4 AV-switch proxy definition. There may be some instances where an AV-switch has some commands that are unique to that specific device, and the defined Control4 proxy does not have a command to natively accommodate that functionality. This functionality will need to be provided to the end user through Composer Pro by means of programming or events. Consider that an AV switch has a command which locks the front panel of the switch so that users cannot change settings directly on the unit. The current Control4 AV switch proxy does not have a command to support this. However, as the driver developer, you can create a command to support setting locking on the front panel in the device-specific commands Lua file found in the template. These types of commands are not sent to the device through Receive from Proxy API, but rather the Execute Command API. As stated above, they are initiated through programming in Composer Pro, such as a button on a keypad or a custom button on a device running Navigator. They can also be tied to events, which can display a pop-up on the UI. To handle device-specific commands successfully, your job as a driver developer will be to define these commands within the device-specific commands Lua file in the template. For example, let's create a command called panel lock. It has a state of unlocked or locked. Once our driver is loaded into a project, the user will be able to schedule the execution of this command or trigger the firing of this command based off of an event. Now let's look at the XML portion of our driver. As we stated earlier, there's only one XML file in our project, driver.xml. Note that the driver XML file name cannot be changed in the template, as Driver Editor expects a driver.xml to be present when it builds our C4Z file. That file is edited through the driver project screen on the right-hand side of Driver Editor. The AV switch for which we'll be creating a driver in this video is the Acme AV switch, so we'll change the manufacturer and model fields to reflect that. Next, we'll name our driver. This entry is important as it will be displayed in places where users will be looking for our driver. A driver name should be descriptive and informative. We'll name this driver Acme AV switch. We'll leave the creator value unchanged for our purposes, but this entry could be a developer name or a company name. Next is the version field. Since this is our first iteration of this driver, we'll leave the version at 1. However, you can start your versioning as you see fit, as long as the version numbers used are integers. We can also update the created entry. This is useful as it provides a date stamp when our driver development was initiated. You can modify the time and date elements by highlighting each and using the arrow buttons. You can also set the field to the current date and time by clicking the plus icon. The modified field functions similarly to the created entry and offers you a way to assign a time and date stamp to future driver modifications. We'll set our modified value the same as our created entry. You can also set the modified date element on a system-wide level under the Tools Options menu. Select dates and you are presented with 3 choices for how the modified field will be populated. Manually, as we have just demonstrated. Upon saving a driver, the modified field will be updated, or you can choose to have the field updated upon publishing the driver. Those are all the changes we need to make to the main page for our driver. All the remaining values are set correctly by default for us from the AV switch proxy template. At this point, we've configured all of the high-level information for our driver. Next, we'll quickly take a look at the proxies. We verify that the AV switch proxy is already added for us, so there's nothing more we need to do here. When we open the capabilities, we see that there are entries for all of the capabilities supported by the AV switch driver template. We can edit a capability by double-clicking on the capability in the driver editor window. This displays the capabilities edit screen. This level of the screen lets us edit the values for any of the provided capabilities. If we save this edited capability, its changes will be included in our driver. Next, we will take a look at the Connections tab. You will notice that the AV switch driver template has 4 pre-populated connections. Also, if we open up the Classes section, we can see that the correct class names are provided. The AV switch template supplies the basic connection information for our driver by default. You will need to add all of the input and output connections based upon the configuration of the switch for which you are developing a driver. At this point, it would be good to discuss how audio-video connections are modeled in Control4 drivers. Each AV connection is defined in XML. This is a static definition, meaning that they cannot be added or changed dynamically from the Lua code portion of your driver. Here are the key XML elements that you will need to include with every audio-video connection. Connection name is the label that appears in Composer Pro. ID is a unique identifier for each connection. Refer to the proxy protocol guide for the valid ID ranges for each connection type. Consumer must be set to true, checked in Driver Editor, for input connections, and false, unchecked in Driver Editor, for output connections. Line level must be set to true, checked, for all audio-video connections. Class refers to the audio or video signal type. To clarify, you can declare an audio type connection and a video type connection. In each of these types of connections, you can declare multiple classes or signal types. For example, you may have an audio input that has both digital coax and stereo analog inputs. This will be defined as one input with two classes, coax and stereo. Up to this point, our discussion of AV connection modeling has been fairly straightforward. I would now like to address a commonly used construct that you may find useful if you are writing a driver that supports both audio and video signal types. For example, if your switch has an input named Input 1, which has audio and video connectors, one would typically consider this one connection. However, in a Control4 driver, you will have two XML blocks, one for the audio signals, referred to as classes, and one block for the video signals. Depending on the type of matrix and the device's protocol, you may wish to consider these connection blocks as related. The way to do this is by using the math formula modulus, also referred to as mod. For example, say that the Input 1 connection mentioned above has an ID of 1000 for the video XML connection block. You would then use ID 3000 for the audio portion of this connection. Both XML blocks would use the connection name of Input 1, since this does not need to be unique. The value of 1000 falls in the range of valid video input connections as defined in the Proxy Protocol Guide, and 3000 falls into the valid range of audio input connections. Now, in your driver, the best way to know that these connections are related is to mod 1000 the ID. When you mod a number by 1000, you remove the thousands from the number. So 3000 mod 1000 equals 0. 1000 mod 1000 equals 0. And 0 equals 0. So we know that these two XML blocks are related and properly model both the audio and video legs of that connection. Finally, we'll include some documentation with our driver, which will help integrators with setting up and configuring the driver. To do that, we'll open the documentation.rtf file and either copy pre-existing content into it or create it right inside the window. The content will be displayed in Composer Pro under the Properties Documentation area for our driver. At this point, we've reviewed and modified all of the key components of our driver project. Driver Editor provides several tools for us to finalize the project and eventually publish it as a working C4Z file. The first step in this process is building the C4Z project file that we've been modifying. The build process does several things. First, it saves all of the files in the project. Then it creates a C4Z file from the list of files found inside the driver editor under our C4Z proj file. To build our project, we'll open the Project tab from the toolbar and select the Build option. Alternately, you can use the shortcut key of F6. When the build of this project is complete, the output window is updated with the results. The next step in our build process is to validate our newly created C4Z file. It is important to understand that a project must be built before it is validated. If you select Validate before building, Driver Editor will force a build of the C4Z proj file to create a C4Z and then perform the validation. The validation step is useful as it leverages a set of generic tests supplied by Control4 and delivered within Driver Editor, which reviews the driver XML file for correct XML structure and valid content. It also compiles all of the Lua files and validates them for correct syntax. To validate our C4Z file, once again open the Project tab from the toolbar and select Validate. F7 will also initiate the validation process. Before validation begins, you can set the verbosity level of the validation process, as well as the level at which logging will be displayed in the output window once validation has completed. Verbosity level gives a listing of the tests that were performed against our driver, as well as their status of pass or fail. Let's select the most option here, as this setting will provide us with additional information in the event that a test fails. We'll select Debug Logging Level, as we like to see any log content that will help us figure out where an issue may be within our driver. Clicking the Validate button begins the process. Here we can see the log file contents of our C4Z validation. The log shows us all of the tests which were run against our XML and Lua code, as well as the results. Using Driver Editor, we've built a C4Z driver from our C4Z proj file. Next, we validated the C4Z for invalid content. Now, we're ready to publish our finished AV switch driver. The publish function in Driver Editor is useful as it places the finished C4Z file in a designated area which can be devoted to completed drivers. You can designate this directory by clicking on Tools from the Driver Editor toolbar. Select Options followed by Workspace. Here you can designate a target directory for building your C4Z proj files into C4Z files, as well as where the publishable drivers will reside. This concludes the template-based AV switch driver development video. We hope that you have found the information presented here informative and helpful in assisting you with developing Control4 drivers for audio-video switches.